Right, this is the 2010 Queensland Senior External Exam for Physics. We're looking at Paper 1, Part B, the short response. This is a knowledge question and it's question 7. First thing we do is we read the question. In a ripple tank operating with 2 point dippers X and Y, waves are created simultaneously. They're in phase. The frequency of the wave is 12 Hz. That's 12 waves per second. Part A. Point P on the water is 12 centimetres and 13 centimetres respectively from X and Y, and it takes half a second for waves from X to reach P. Determine Part 1, the velocity, and B, the wavelength of the waves. Part B of the question, does P lie on a nodal or antinodal line? Explain your reasoning. 2 plus 2 marks, so 2 marks for question A, 2 marks for question B. Okay, we've read the question. Now we need to go through the question and identify all of the important bits of information. So X and Y are our 2 dipper points. The waves are in phase and I've got a frequency of 12. There's a point P on the water and it's a certain distance from each one of X and Y, and it takes the waves half a second to reach P. We need to determine the velocity and we need to determine the wavelength of the wave, so that's part A. And looking at part B, we want to know whether it's a node or an antinode, and we need to explain. Okay, we've gone through and we've identified the key pieces of information in the question. Next question now, our next part now is to draw a diagram. Okay, so we've got 2 point sources like so. We'll call them X and Y. They're both making waves going out, so there's waves coming out from this side, there's waves coming out from that side. The waves are going to interfere with one another, and we have a point P. It's 12 centimetres from X, and so here's our central line. Along that line will be equidistant from X and Y, and so if we're 12 from X and 13 from Y, our point P is going to be slightly above that line. And so if I were to dot that distance there in to P, that would be a distance of 12 centimetres. If I were to dot that distance in there, that would be a distance of 13 centimetres. Okay, now if we do a little bit more work on this, we have a frequency of 12 Hertz. 12, let's get that decimal point there nice and clear. And it takes half a second for waves to go from X to P. So from X to P takes a time of 0.500 seconds. Okay, we've drawn our diagram like so. We now need to decide how we're actually going to go about and solve this problem now that we've got all of this information written down. So the first part, we want to determine the velocity. So A, part 1, after velocity. And if we have a look here at our formula sheet, there's quite a simple formula for velocity, which is right here at the very top of our sheet. Velocity equals distance over time. So let's go through now that we've decided how we can actually go about this. We now need to lock in our values. And our distance from X to P, S from X to P equals 12 centimetres. And the time from X to P equals half a second. So if we put those values in here, 12 centimetres divided by 0.500 seconds, that there gives us a velocity of 24, now to 3 significant figures, metres per second. Let's have a look and make sure. So our distance 12 has 3 significant figures, and our time 0.500 has 3 significant figures, and therefore our velocity should also have 3 significant figures. So the velocity of the wave is 24.0 meters per second. That's A part 1. Let's have a look at A part 2. A part 2, we want to go through and we want to work out the, now let's make sure we've got it right, the wavelength of the waves. So here we were after V, now we're after wavelength. Let's have a look at our formula sheet again, and there's quite a simple formula for velocity, frequency and wavelength. V equals F lambda. So we can write down V equals F times lambda. In this particular question though, we're after the wavelength lambda. So lambda, if V equals F times lambda, lambda equals V over F. And so our velocity we just worked out to be 24.0. Our frequency is 12 Hertz. So we go 12.0 for Hertz, and therefore we get our wavelength here 2.00, and our distance is in centimeters. So therefore the wavelength of the waves is 2.00 centimeters. Note that we've done that to 3 significant figures as well. So we've done part A, part 1, part A, part 2, and now part B. Does P lie on a nodal or an anti-nodal line? Explain your reasoning. So what we want to do is we want to calculate the path difference. If the path difference is a whole number wavelength, it's a antinode, which means it's constructive. So a wave meets a crest meets a crest, a trough meets a trough. If the path difference is a multiple of half a wavelength, that's n minus a half wavelength, then it's on a nodal line and it's destructive. And so what we need to do is we need to calculate our path difference. So the path difference is going to be equal to yp minus xp. Yp minus xp. So yp is 13.0 minus xp is 12.0. When we do that, we get a path difference of 1 centimeter. Our path difference is 1 centimeter. The wavelength of our waves is 2 centimeters. So that is actually half a wavelength. Okay, so if our path difference is half a wavelength, then the path difference, then it is a nodal line and it's destructive interference. So P lies on a nodal line as the path difference equals lambda on 2. There we go with our answer for question 7. Now, overall worth 4 marks, so 1 mark for this question, 1 mark for this question, 1 mark for saying whether it's on a nodal line, and 1 mark for the explanation.